So this is going to be quite a change. I see Jörg already has a question on my talk. Jörg, can you? Okay. It's going to be quite a change of gears from Pascale's talk. It's going to be a simple experimental talk. I see that most people here are quite theoretical, but I hope I provide some entertainment. So I have two stories today, and both are based on a sort of simple experimentally, at least conceptual idea, to have a homogeneous 2D Bose gas made in an optical box trap, as cartooned here, and just shake it with an uniform but time varying oscillating in plane force. Okay. And basically the difference between the two stories that I'm going to tell you is just, in essence, the big difference is just how hard you shake. Okay, so the first story, which is already published in this Nature from this year, is on linear response, and this is on the first observation of first and second sound in a BKT type superfluid. And the second story, which is still preliminary, is currently called the birth of 2D wave turbulence, and it is about basically how turbulence emerges in the system as you shake harder, and we try to view this on kind of all relevant time scales and length scales, which is not what you can usually do in traditional systems where you study turbulence. And here on the left are the students, and on the right the postdocs who did this work. For both of these stories, it is essential that the gas is homogeneous, so there's no harmonic trap, just like in Emmanuel's talk this morning, and I saw in chat that Jörg is also saying for his new general hydrodynamics experiment, it's also essential for many modern experiments. This is quite important, but I'm not going to go much into technical details of box traps. I just want to briefly advertise if people are interested that recently with Nir and Rob, we wrote a little review which should soon be in Nature Physics on various modern experiments where boxes matter. This is just a gallery of various systems, including Jörg's here in 1D, starting with our simple 3D Bose gas, and actually more recently it's Emmanuel doing it for molecules as well. And in between it has been done for both bosons and fermions in various dimensionalities. So I start with the first story, which is the first and second sound in a BKT superfluid. So there's kind of two parts to this title, and I'm going to give one slide on each as a bit of a background. For most people here, this might be very familiar, but it bears repeating. So the first background slide is on BKT phase transition in 2D. So this is a topological phase transition associated with binding or unbinding of quantized vortices of opposite circulations, depending whether you go to low or to high temperature. It's an infinite order phase transition that doesn't involve any symmetry breaking, so no Bose-Einstein condensation in our context. There's a change from just algebraic decay of correlations to exponential decay of correlations below and above TC, respectively. So almost nothing happens at this phase transition, except superfluid density emerges. But that one thing, is kind of more dramatic than in the conventional sort of Landau-Ginzburg second order phase transition. So superfluid density is actually supposed to exhibit a so-called universal jump. It is universal in the sense that when you make it dimensionless, if you look at the superfluid phase space density and as times lambda squared, where lambda is a thermal wavelength, then it is to jump from 0 to 4 at the critical point, instead of growing smoothly as, say, for example, a conventional Bose-Einstein condensation in 3D. So this was predicted by Nelson and Kostowitz back in 1977, and it was observed almost immediately by Bishop and Rappi in 78 in this torsional pendulum experiment, where they basically look at the change in the drop in the moment of inertia below the classical value. Now, on the other hand, as some of you will know, with cold atoms, we've been studying BKT physics for about 16 years now. And there have been many complementary experiments, things you couldn't do in liquid helium, directly observing vortices, studying coherence properties, measuring critical velocity, and so forth. But actually, no measurement of superfluid density. So the first thing that was done in helium, we couldn't do until now. That's the first background slide. And the second background slide is on something even older, which is the story of first and second sound. And this, I guess, is very familiar to many people here who are interested in hydrodynamics. So this goes back to to Titze, and maybe not Titze in the quantitative sense, to maybe to Landau to 1941, but essentially to discovery of superfluidity in 3D liquid helium. And so there, it's essentially incompressible liquid, and the first sound is an in-phase oscillation of the normal and the superfluid components is just a density wave like the one we used to talk. And the second sound is a pure entropy or temperature wave, where the normal and superfluid densities oscillate out of phase. But the key point is that because you have a superfluid, you get two sound modes with two different speeds instead of one. And this again was observed very quickly, just in a few years, in 3D liquid helium. And then more recently, it was also seen in 3D superfluid atomic gases, both Bose and Fermi, first in Rudy's group in Innsbruck, and then also at Martin's, Zurlein's at MIT, and mine in Cambridge, for both bosons and fermions. The one difference here is that even unitary gases are somewhat compressible, at least. And so both of these modes actually couple to density, which means you can take pictures of them, right? So that's an experimental advantage. But still, the essence is the same. There's some kind of rotation, of the basis, but still the idea is like if you have a superfluid component and normal component, you get two sounds. And so now we come to our story and the motivation for it. So it's kind of a twofold motivation. The first one is that the sound speeds give the superfluid density. If you're in liquid helium, actually, you just need a second sound, but if it's a compressible liquid, you need both in order to extract both speeds to extract the superfluid density. So that's good for us. That's why we want to do it. And the other kind of motivation selling point is that the first and second sound were actually never observed in any 2D BKT superfluid, because in helium they can't do it because of basically the no slip condition. Right? So the normal component is pinned to the substrate. Right? So neither first or second sound actually propagate in liquid helium films. And so I think Landau would have liked this story because he never liked Bose-Einstein condensation. His point always was that the superfluidity is a more general hydrodynamic phenomenon that is not conceptually linked to BC. And so I think he would be pleased to see it in a BKT type superfluid where superfluidity is not intimately tied to condensation conceptually. All right. So that's the twofold motivation. And now we go to experiments. This is our setup, which I just flash briefly. As I said, I don't want to talk much about how one makes these box traps. They're relatively common now, and this one is not that special in any particular way. What is important for the experiment is that we use the Feshbach resonance in this potassium-39 gas to make the gas relatively strongly interacting. Okay, this dimensionless G is a measure of interaction strength, and basically 1 is super strong, and 0.1 is weak, to give you a sense of scale. And this is important because in order to see this, two fluid model physics, you have to be hydrodynamic in a classical collisional sense. It is not enough to have superfluid hydrodynamics for the superfluid component, but the normal component has to be collisionally hydrodynamic. And so there was actually a previous experiment in Paris in Jean Dalibard and Jérôme Bignon's group, where they tried to do essentially the same thing, but just the gas was too weakly interacting, and so this two-fluid hydrodynamic behavior is not seen. It's something more also interesting, but more complicated. Some kind of collisionless gas, the sound propagation is observed. So we observe, with Bose gas, you cannot go super strongly interacting because you get 3 body losses, but if you go strongly interacting enough, the collision rate is several times larger than the oscillation frequency. That turns out to be enough. But at the same time, the gas is quite compressible. Okay, so again, we can see both things in density response. And so, as I said, the idea is simple. You have some in-plane force, which is spatially uniform and just oscillates back and forth. And so that basically couples directly only to the lowest sound mode, just a standing wave, which has the longest possible wavelength in the system, or wave vector pi over L. It leads to this kind of sinusoidal modulation of the density, and then the amplitude of this modulation oscillates in time. Okay, so you can just measure this B1 of t, or basically just look at the displacement of central mass because they're trivially related to each other. So this is just some example of the data. You see how the central mass oscillates. There's a part that oscillates in phase with the force, and the part that oscillates in quadrature. Formally, the part that oscillates in quadrature gives you the imaginary part of the density response function. That's what gives you the resonance. It's basically where the velocity peaks. Okay, and so first, some qualitative conceptual ideas. Again, the key point here is we're exciting a single wavelength. Okay, and so when you know your wavelength, then the resonant frequency gives you directly the speed of the sound. Okay, and if you see more than one resonance, that's possible only if you have more than one sound. That's a basic message. And so these are data at low, something that I for now call just low temperature and high temperature, and everything is made dimensionless using some natural Bogoliubov units. And so at low temperature, indeed, you see 2 sound modes. The first sound is the one with the higher frequency, The nomenclature comes from the fact that if there was a race, the first sound would get there first, because it has a higher speed. You also see these things are quite broad. That's related to what I said in the previous slide, that like, we're not that deeply hydrodynamic because it's very hard to do with the Bose gas. So if you had infinite collision rate, which you can't actually have even in a unitary gas, then this would be almost delta function. There will be still some fundamental limit of diffusivity, which is like h bar over m, but they will be much sharper. But in our case, we go as strongly tracking as we can afford to, without having too many losses, and that's enough to resolve this curve. But they're still relatively broad. And then at the high temperature, the first sound is still there, and you see there's actually some kind of shoulder here on the left, and I won't go into detail of that today. But that's actually the overdamped diffusive heat mode, which is what the second sound turns into above the critical temperature. So these are two separate, just two different temperatures right here. You can now study it like for a range of temperatures, and for all temperatures you can check that your spectrum satisfies the so-called F sum rule. This is just telling us that we haven't missed the resonance somewhere else. Okay, so when we say like there's only one mode above TC, like the fact that the sum rule is exhausted tells you that there isn't somewhere at the higher frequency and we just forgot to look. And the sum rule, has various contributions, from the first sound and second sound below TC, from the first sound and the diffusive mode above TC. But where the second sound disappears is where the critical temperature is, and so you can also check that that agrees with the BKT predictions within our systematic errors. So this part is kind of, one can do without too much theory. I mean, there's some, formulas you can look up for the sum rule and for the critical temperature in the BKT theory, but that, it's not very theoretically involving. Now, I come to the summary of the main results, and this involves quite a bit of theory. So to compare, our measurements with some theory, what you need is basically, Landau's original equations, which are general. But then you have to feed into them some theory of the thermodynamics, okay, which is hard for BKT. And this comes from Prokofiev and Sisson of various papers, but this is sort of the good starting point if one wants to look. And one needs to put in the theory of what the superfluid density is in order to predict the sound speeds as well, okay, which again comes from them. And then one needs to combine all that, which was in a series of papers, but again, this is a good starting point if one wants to search, done by Sandro Stringer. And so I'm going to show you three graphs, which are actually in many ways the same. It just depends, where you're coming from and what result and what kind of comparison you find most pleasing. So the first one is you just measure the speeds of sound. First is red, second one is blue, and compare it directly with the theory that comes out of these calculations. And so that looks pretty good. We know that here at very low temperature, the theory is wrong for some reasons that are understood, but not important here. And there's a discontinuity in both first and second sound speeds because the superfluid density is discontinuous in the theory. Discontinuity in first sound is obvious. In the second sound is obvious. The first sound is small and kind of comparable to a data scatter. So it's maybe just fortuitously suggestive that we see that. That's one way to look at the data. The other way to look at the data is to say, okay, thermodynamics we know. So either I'm putting in superfluid theory density and comparing the sound speeds, or I take my sound speeds and extract the superfluid density and compare that way. So this is then the superfluid fraction as a T over TC. Again, this is a theory without any free parameters. But this is not the graph that is universal. So this jump in NS over N depends on the interaction strength, J tilde. And so I'm going to show you a third one where we just make it in terms of superfluid phase space density, because then the jump is 4. Okay. So this is the superfluid phase space density versus total phase space density normalized by the critical value. So the transition is at 1, and now the jump is 4, and then it relatively quickly goes towards 100% superfluid fraction, which is shown by the dashed gray line. One additional reason I like this this last graph is because you can add a qualitative line. It's not really any theory, but it's kind of good for intuition, which is how the superfluid density would grow if this was a BEC-like transition. Okay. So for BEC-like transition, at some point you have saturated the normal component, everything else goes into the superfluid. So of course this transition doesn't exist in 2D, but like in this graph you can't see that. So when you look in terms of phase space densities, if there was a critical phase space density for a BEC-like transition, then the superfluid would grow according to this red line, and you see that in reality it grows very differently. Essentially instantaneously, most of the superfluid gets converted, most of the fluid gets converted into superfluid. So that is the end of the first story, and I want to switch to the second story, which is more open-ended and more non-equilibrium. So more related maybe to this workshop. This first slide is just to wake people up to see that something new is starting. I will come back to explain it. It makes some sense. Okay, you see some flow of stuff, over length scales, and that's important for turbulence. So again, a bit of a background here. I'm going to start in 3D, and about 100 years ago. By the time this paper comes out, it will be nicely exactly 100 years. Well, hopefully it will come out in 22. So in turbulence generally, and starting in 3D, this is a non-thermal steady state, okay, as most people here know. And the key concept is the so-called cascade of energy, or could be some other excitations across length scales with some scale invariant fluxes. This is for direct energy cascade, which was conceptualized by Louis Richardson, who's a mathematician and also cared about the weather. In this poem, where he actually paraphrases Jonathan Swift, big worlds have little worlds which feed on their velocity, and little worlds have lesser worlds, and so on to viscosity. So the idea here is that you somehow inject energy in the system at a large length scale, and then without any loss, it cascades, through various length scales until it reaches some small length scale where it is dissipated, which in a classical fluid is set by the viscosity, which we don't have in that conventional sense in our system. But as we have shown in some earlier work that I don't go into here, in our case, this viscosity is essentially replaced by the trap depth. That's the only thing that takes the energy out of the flow. Okay. That's the only cut-off there is. Everything else is seen, everything else is preserved inside the box. And we actually look not at whirls, which are vortices, but at waves. But still, these concepts of the cascade universe. And so the key signature of such a cascade, of all turbulent cascades, is some kind of power law distribution in momentum space. And so this is now 5 years old in 3D homogeneous Bose gas. We saw such a power law distribution as a signature of the cascade with an exponent of 3.5, which is close but distinct from the simple analytical Kolmogorov-Zakharov prediction for so-called big wave turbulence, which is gamma equals d equals 3, where d is dimensional. And it is understood, at least qualitatively divided differences might be there, but it's not important for this talk. Now, the second part of the background is we're going to work in 2D now, and 2D is actually, maybe most famous to most people for the fact that it also supports an inverse cascade, which goes from small length scales to large length scales. That's why we have weather, for example, apparently. And there have been some examples of experiments on that in homogeneous 2D Bose gases with vortices, where so-called Onsager-Waldrich clustering was observed. But we're going to stick to what we know, which is the direct wave cascade. So if you thought that 2D supports only inverse cascade, that's not true. Depending on your injection protocol, anything can happen. And so we're doing a direct 2D wave cascade. I come back to this drawing, which looks like a flow of stuff, in this case water, from small to large length scales, but that's because I didn't tell you that I'm doing it all in K-space. Okay, so this is actually our direct cascade, where the energy is injected at some small momentum, which is the inverse system size. Is that same shaking that we did in the first part of the talk, and is dissipated when the water just leaves our 2D table, right? At the trap depth, and somewhere in between, the nature of the excitations at 1 over xi. Xi is the healing length, also changes from phonons to particles. And so just to show you that we're in business, that we can study turbulence in the system, I'm first going to show you the steady state. So basically, this is kind of what was done before in 3D, and it looks similar, except the numbers are different. There's some experimental considerations here. So, to keep the dynamics two-dimensional. Okay, sorry, I did it the other way. So first of all, you want to put in a lot of kinetic energy in the system, more than there was original interaction energy. So you have the turbulent flows dominated by the kinetic energy, which means that the trap depth, which is the energy cutoff, should be somewhat significantly larger than the initial chemical potential. But at the same time, we want to restrict the dynamics to 2D, okay, which means that the trap depth should not really be much larger than the thing that confines the atoms to the plane, the tropic frequency that confines the atoms to the plane. All this modulo, Jorg's paper from 2 days ago, which I haven't read yet, where he says that this is maybe more forgiving, that maybe don't have to be so strict. But still, UD should be comparable at least to H bar omega z. And so to satisfy both of these, now we go weakly interacting. For the first experiment, it was good to go strongly interacting. Here we're going to go to G below 0.1 in order to have this range. And so we shake strongly. Strongly means that the potential drop across the trap is of the order of the chemical potential. That's the scale that sets whether something is strong shaking. And relatively quickly, faster than in 3D, the cascade fills up, and we see this power law momentum distribution up to the dissipation scale. This point is now 2.85. We don't know how to predict that number. It's different from d equals 2, which is a simple theory. It's also different from d equals 3, which is a simple theory for 3D, and it's different from the 3D experiment. Okay. This is interesting for the theorists to explain, but as you will see for the end of my talk, in some sense, it is nice that this doesn't fit simple theory, because it will show you that some conceptual ideas related to the birth of turbulence are more robust than the specific predictions for the gamma. And this gamma itself is robust. We have varied things like interaction strength, chemical potential, density, strength of driving. It always comes out the same. So experimentally, it is trustable. And what you see here sorry, I forgot to say in the bottom inset, is just the so-called compensated spectrum. So this is a power law. If you just multiply by k to the gamma, then it looks flat. Okay? That's just a conventional way of presenting things in turbulence. Okay, so now we come to the new stuff. So this is the same as in 3D, just the number is different. Now, this is the new things that we couldn't see in 3D for various experimental reasons. So there's two more concepts related to how this, how this turbulent steady state forms. Okay? Generally, if you look across systems and decades, much more is known, about what turbulence seems to be in steady state than about how you actually reach such states starting from equilibrium. Okay? And so this is something that we can do in the system because we can probe it, on all relevant timescales and length scales. So the first concept in the emergence of turbulence is so-called emergent isotropy, not so-called, it's just emergent isotropy, which means that generically you will pump energy into the system some anisotropic way. In our case, this would be obvious, but in general systems, it will generally not be isotropic. But then, at least under some conditions, whatever the microscopic interactions are, which are also not local in K-space in general, certainly they're not for our Bose gas, beyond some sufficiently large K, here in blue, you're supposed to see some emergent dynamics which are isotropic and local in K-space. Okay, and so if I can allow myself to stretch my water in K-space analogy even further, it should look like something on the right. Okay, that locally at low K you can see that something is clearly anisotropic, but if you look at large enough K, you can it looks all isotropic. All right. That's the first concept. And the second concept we have heard about today, and many people here are very familiar, are organizers, which is the dynamic spatiotemporal scaling. So once you have the isotropic cascade, the way it propagates before steady state is established, right? The expectation is that this cascade front propagates as t to the minus beta, t's time is beta is some exponent, and that in its wake, it leaves this what will be a steady state distribution k to the minus gamma, okay? So put those two things together, it should look something like this. It's a sort of self-similar, propagation. This is just some 3D simulation, but it would look qualitatively like this as well in 2D as well. And so this is actually, just another example of this general, form of self-similar spatiotemporal of dynamic scaling, which seems to be all over the place. We have heard about it in Manuel's talk in the context of Carré-Parisi-Zhang equations. It is widely discussed in the context of non-thermal fixed points that, again, Jorg and other people organizing this conference know a lot about. It's just that these exponents alpha and beta are different in different cases. Okay? But this form that originally comes from classical surface growth is all over turbulence, and now speculated to be more generic to far from equilibrium quantum systems. These exponents alpha and beta are never independent. There's always some physics between them, and this physics could be like, what is the conserved quantity, what is the dimensionality, what is the dispersion relation, things like that. In our particular case, we have the self-similar propagation. You have alpha equals gamma beta. That's sort of trivial graphically. And then beta is also related to this cascade exponent gamma through essentially energy conservation. This is the same expression for any d. Okay, in our case, it's going to be d equals 2, but it will be the same expression for different d. And so we want to see whether we can see these things. Okay, and so here's the experiment. Still concepts. So first of all, our injection is manifestly anisotropic. Okay, here we have our 2D box. Okay, so it's a uniform gas at energy mu. Energy is vertical. At UD, there's going to be some dissipation. We shake it by force, which goes along one of the two directions. Okay, and so that excites this phonon mode, which looks a bit like a French flag. Which is clearly, along the shaking direction. Why? Okay, but then at high K you see something isotropic. So the question is, what happens in between and when? At least we want to see it, if not understand it. Understanding might be a job for the theorist later on. And to do that, we're going to use 3 complementary experimental tools, which allow us to see things at different length scales. So down here at the smallest k, we resolve individual, discrete states such as this one using what is called the principal component analysis. Okay, it's machine learning basically, if you want to be fancy these days. And then intermediate length scales, we use Bragg spectroscopy, which doesn't quite resolve individual states, but it is good all the way to k equals 0 without suffering from issues such as finite size of the system and so forth. And then at high k, we use the time of flight expansion, which is what I've already used to show you the steady state. And so we're basically going to have, I don't know how I'm doing with time. Okay, I think I'm fine.
4 minutes left.
5, yes? Yeah. Okay, so we're going to have basically 3 slides for each of these tools. And so at low k, actually, we do not see emergent isotropy. We see persistent anisotropy. Okay. So we can resolve up to 4, maybe we can push it to 5 of this low k phonon modes directly in situ from the test response. Green is the direct driving, okay, and then the nonlinearity propagates the energy to higher k, to smaller length scales, but it all seems one-dimensional, which is maybe nice because maybe you can actually study one-dimensional physics in this native 2D system, right? Just because the dynamics need to be protected somehow at small enough k. One can also look at the time variation of these modes, which is important in 2 ways. First, it shows you that this is not just off-resonant excitations; they actually oscillate at harmonics. So there's a nonlinear combination of phonons into higher energy phonons, and you can maybe also see some delay. It's all very fast dynamics; it all happens within one shaking period, but you can still maybe see that there's a delay between the occupation of the driving and the occupation of the higher k modes. You can also look at the amplitudes of these things. That they are maybe also power law, but we don't know why it should be and what the theory for this would be. But anyway, so there's maybe some kind of 1D acoustic wave cascade going on. It's very low k. So then we'll go look a bit higher, with the Bragg spectroscopy. Now, Bragg spectroscopy, for those of you who don't know, essentially integrates the momentum distribution along one direction. Okay, so we do 2 separate experiments. We either look parallel to the shaking or perpendicular to the shaking. Okay. And so because you have this anisotropy at low k, but isotropy at high k, what you want to see is, at low k, the 2 directions are different, but the wings are the same. Okay. And so indeed, this is what you see already after one shaking period. The low k anisotropy is not a surprise anymore, given what I've shown you from the PCA. But it's sufficiently high k, above 1 inverse micron or so. When excitations first reach there, they're already isotropic. They're already reaching, simultaneously in x and y, or in parallel and per. And meanwhile, at k equals, this is just after one shaking period, but at k equals 0, the anisotropy persists forever, at least until when we're in steady state, the anisotropy is still basically the same, or within a factor of 2, whatever, as when we start. Okay, so we have low k clear anisotropy. We have emergent isotropy at some length scale, which is most probably set by the healing gland. We have some qualitative understanding of that. And then beyond some k of the order of inverse micron or half inverse healing gland, we can start looking at TOF and trust that this is a proper isotropic distribution. Between this length scale of 1 over psi and the dissipation scale, there's still some way to go. And so this is where we look for the dynamic scale. So now the cascade front has formed. We have an isotropic distribution. We want to see how it propagates in time. So this is essentially zooming in on the cascade front, and it's mostly pre-steady state, except the last orange data, which is actually already in steady state. And it's a composited spectrum, which means that basically we have taken alpha and gamma to 0, and the beta is the only exponent that is left to matter, which determines the other 2, if you like. And so now I can just predict, okay, theoretically, that the speed of this front, it's not a constant speed, but the scaling of this front, cascade front, should be t to the minus beta, and that the beta should be minus 0.87. Now, I want to clarify what I mean by predict. This theory, the equation is general. It involves some unknown gamma, the dispersion relation, which I know is quadratic because I'm below the healing gland, okay, and I put in the dimensionality. Okay. Now, theorists expected gamma to be 3, and hence they expected beta to be minus a half, but gamma is not 3. So what I say by predict, I mean that I trust this general principle more than the specific prediction for gamma. So take the experimental gamma at face value and say, if this scaling concept is stronger, then the consistent beta has to be minus 0.87. And this turns out to be the case. Okay, so here the theory is just drawn. Okay, this is the theoretical prediction. So this is what the cascade front follows until, of course, it hits the dissipation scale. Then it has to saturate there. Then it's stuck there. Or I could turn this around and fit the dimensionality as a free parameter. Okay, so I have the experimental gamma, I have the experimental beta. In this case, I just get something consistent, but it's something, this 2.1 plus minus 0.2. But this is conceptually maybe interesting for the future because one can study various dimensional crossovers and basically fit. D becomes a free fit parameter, and you can study dimensional crossover using this. Maybe. I mean, we have not done it yet, but it's maybe an interesting idea for the future. And then finally, as the last point, which is not surprising given that this graph in the middle works, with this beta, I can collapse all these curves until the steady state is reached. Okay, so we see the working of the scaling solution, until you go into saturation, and when you go into saturation, then the scaling breaks down. In theory of the the non-thermal fixed point story, the scaling breaks down once you approach some equilibrium state. Here you're not approaching equilibrium state, you're approaching a stationary non-thermal state, but still the same ideas extent. And so with that, I hope I didn't run over. With that, I am done. There's two stories. First one about linear response, and very old story about seeing the universal superfluid density jump in a BKT superfluid, also seeing the first and second sound for the first time in any BKT superfluid. And the second story is still, well, we're still digesting it, but it is about how, by looking at turbulence at all length scales, you can see various conceptual ideas, conceptual things about how it is birthed, how it forms. Thank you very much for your attention.